In this video, we're going to cover section 8.3 on acid-catalyzed hydration. Now, when we treat alkenes with water, the resulting addition reaction is referred to as hydration. Now, the addition of water across a double bond in the presence of an acid is referred to as an acid-catalyzed hydration. And this reaction also proceeds via Markovnikov addition, as we saw for hydrohalogenation of alkenes in the absence of any alkyl peroxides. This will be one of three different ways in which we will look at the addition of water across the double bond. And what you see in this particular example is if we start with an unsymmetrical alkene, and if we add water to it in the presence of a small amount of acid, the major product of this reaction is an alcohol. So this is a transformation from alkene to alcohol. And note that the hydroxyl group, which is the functional group for alcohols, is directly attached to the more highly substituted carbon of that original alkene. Now, there are a couple ways in which we can show that the reaction is acid catalyzed. One way is to show the hydronium ion on the reaction arrow, which implies that it's water is the main reagent used in this reaction, but there is some acid present. And so in the addition of acid, you'll generate small amounts of the hydronium ion. Another way in which you can show that the reaction is acid catalyzed is to show in brackets a strong acid. In this example, they're showing sulfuric acid is being used as the acid in catalytic amounts. So as we said, the hydroxyl group is added to the more substituted carbon of that alkene. And the more highly substituted the carbon is, the faster that this reaction will proceed. And so this will have a lot to do with the relative stability of the intermediate. And no surprise, a carbocation intermediate will be more stable when there are more substituents attached to it. And so you can see for a simple ethene versus propene, and then this 2-methyl propene, that the rate increases a millionfold as we go from ethene to propene, and even a further factor of 10 to the 5 if we go from the propene to the 2-methyl propene. So again, the more highly substituted a carbon center is of an alkene, the faster this reaction will proceed. Now, if we look at the mechanism for this reaction, it proceeds in much the same way that we saw for hydrohalogenation. The first step is a proton transfer, and no surprise, the proton transfer is going to come from that acid present in the reaction mixture. So as shown, we're using the hydronium ion to represent that acidified water. And so the hydronium ion is acting as your acid, the alkene again acting as your weak base. And so the proton transfer results in the formation of a carbocation. So the carbocation that's formed will be the more stable of the two options. So you look to the substitution on each carbon of the alkene, and the more highly substituted carbon will be the carbocation carbon after that proton transfer step. So just to clarify, yes, a water molecule is also produced in this step, this proton transfer step. That water molecule now, as there are many in this reaction mixture, but a water molecule will then act as a nucleophile to attack that carbocation. The intermediate that you form at this point is yet again an atomic center that has a formal charge of +1. When that atomic center is oxygen, we refer to this as an oxonium. And so that's what we form after nucleophilic attack. We form the oxonium. And it's this oxonium that will become the alcohol once we complete our mechanism with a final proton transfer step. Being copious amounts of water present in this reaction mixture, water will also act as the base in this particular reaction. And so it will act as a base to remove a hydrogen as a proton from that oxonium giving back oxygen to lone pairs and giving you the neutral alcohol. And yes, as a result of this reaction, this final proton transfer step, we also form a molecule of H3O+, which is the same reagent or species that was involved in that initial proton transfer step. This is why we refer to these reactions as being catalytic, in that the catalyst is not used in the reaction in the sense it's not ending up in the product. The catalyst is used to initiate the reaction, and it's reformed at the end of the reaction. So this hydronium can continue to react with other alkenes in the reaction mixture. And so this is why we do not need molar amounts or significant amounts of H3O+ in a reaction mixture, because it's regenerated in each reaction with the alkene as it proceeds to the alcohol. A couple other points, or one final point to make, is that notice how we're using equilibrium arrows in this particular mechanism. And that's because depending on the conditions of the reaction, we can favor either the formation of the alcohol, as we showed in this reaction, or if we were to remove water from the system or concentrate it with more acid, we can force the formation of the alkene. And this reversibility really depends on the nature of the reaction conditions. And so you may recall that this reverse path, starting from our alcohol in the presence of an acid catalyst, forming the alkene, this conversion from alcohol to alkene is the E1 reaction. In fact, we refer to this as an acid catalyzed dehydration, because we're removing a molecule of water, or a water molecule is formed in the process as we convert this alcohol to the alkene. So this equilibrium is sensitive not only to temperature, but also to the concentration of water present. So under conditions where we're only using small amounts of acid, meaning there is copious amounts of water present in the reaction mixture, the major product will be the alcohol. So the equilibrium will favor the formation of the alcohol. However, if we were to decrease the amount of water present in the reaction mixture and use concentrated amounts of acid, then we're going to convert the alcohol to the alkene. And so the equilibrium will favor alkene formation. So we need to choose appropriate conditions depending on which type of transformation, which product we wish to form. Now, similar to what we saw for hydrohalogenation, there is a stereochemical aspect associated with hydration as well. So if we generate a chiral center as a result of hydration, we should recall that we will form both the R and the S enantiomers, because again, having a carbocation intermediate, it's open to nucleophilic attack by water from either side of the plane associated with that carbocation intermediate. So if in fact a chiral center is formed, as shown in this example with 3 different R groups, we will form in a 50-50 mixture, a racemic mixture, will form R and S enantiomers for this particular reaction. So as you can see in this particular example, if we were to start with this unsymmetrical alkene under acid catalyzed conditions, acid catalyzed hydration conditions, we would form these 2 alcohols, and we would form them in a 50-50 ratio. So this is one of 3 ways in which we can hydrate an alkene. If you have any questions about acid catalyzed hydration, by all means, send me an email. Thank you.